Parts like pistons, valves, and connecting rods are moving so fast that mechanical stress rises sharply. In most modern passenger cars, the red line typically falls between 6,000 and 7,000 RPM, while high-performance engines can safely spin even higher. What many drivers don't realize is that red line isn't about instant failure. It's about long-term survival. Briefly touching red line during hard acceleration is usually fine, but living there dramatically increases wear and heat. That's why the red zone exists. It's a warning that performance has a price: fuel. Fuel is the energy source that allows an engine to do its job, turning chemical energy into motion. In gasoline cars, fuel is mixed with air and ignited thousands of times per minute, releasing controlled energy that pushes the pistons downward. What many drivers don't realize is how small the actual fuel flow is. At highway speeds, an engine may consume fuel at a rate that could fit through a drinking straw. Fuel quality also matters more than people expect. Using the correct octane rating helps prevent engine knock and ensures the engine performs as designed. Without fuel, even the most advanced engine becomes useless, which is why fuel efficiency and range remain critical factors for everyday driving. All oil is what keeps an engine alive under constant stress. Inside a running engine, metal parts are moving thousands of times per minute, and without oil, friction would destroy them in seconds. Engine oil forms a thin protective film that reduces friction, carries heat away from critical components, and traps microscopic debris. What surprises many new drivers is that oil doesn't just wear out, it breaks down chemically over time. High temperatures, combustion byproducts, and shear forces slowly reduce its ability to protect the engine. That's why regular oil changes matter far more than most people think. Skipping them doesn't cause instant failure, but it quietly shortens an engine's lifespan every mile you drive. If you want a deeper breakdown of oil types, weights, and what your car actually needs, I've linked a full guide in the top right corner of the screen. Coolant is what keeps an engine from destroying itself with heat. When fuel burns, temperatures inside the combustion chamber can exceed 4,000 degrees F, far hotter than metal parts can survive. Coolant circulates through passages in the engine block, absorbing heat and carrying it to the radiator where it's released into the air. What many drivers don't expect is that coolant does more than just cool. Modern coolant also prevents corrosion, lubricates the water pump, and protects the engine from freezing in cold climates. Running low or using the wrong coolant can cause overheating, warp components, or even engine failure. In other words, coolant quietly controls whether your engine survives extreme temperatures or not. Radiator. The radiator is where an engine finally gets rid of its heat. After coolant absorbs extreme temperatures inside the engine, it flows into the radiator where thin metal fins expose that heat to passing air. At highway speeds, airflow alone can do most of the cooling, while electric fans step in during traffic or idle conditions. What often surprises new drivers is how efficient this process is. A modern radiator can dissipate tens of thousands of BTUs of heat every minute, quietly keeping temperatures stable without the driver noticing. When a radiator fails or becomes clogged, overheating can happen fast. That's why this simple-looking component plays a critical role in keeping an engine alive under real-world driving conditions. Battery. The battery is what wakes a car up before the engine ever starts running. It supplies the electrical power needed to crank the starter motor, fire the ignition system, and bring the car's electronics to life. In most gasoline cars, the battery operates at around 12 volts, delivering a short burst of high current that allows the engine to start in just a second or two. What surprises many drivers is that once the engine is running, the battery takes a back seat. Its job shifts to stabilizing voltage and supporting electronics while the alternator handles most of the power generation. A weak battery doesn't always mean a dead car. It often shows up first as slow starts, dim lights, or unexplained warning messages. Transmission. The transmission is what decides how engine power actually reaches the wheels. An engine can only operate efficiently within a limited RPM range, and the transmission constantly adjusts gear ratios to keep the engine in that sweet spot. At low speeds, lower gears multiply torque to get the car moving. At highway speeds, higher gears reduce RPM to save fuel and reduce wear. What surprises many new drivers is that without a transmission, even a powerful engine would be nearly useless. The car would either stall at low speed or over-rev at high speed. In everyday driving, the transmission quietly works behind the scenes, shifting hundreds of times on a long trip to balance performance, efficiency, and durability. An automatic transmission shifts gears for you, deciding when to change ratios based on speed, throttle input, and driving conditions. Instead of a clutch pedal, it uses systems like torque converters or internal clutches to smoothly manage power delivery. In everyday driving, this means you can focus on steering and traffic while the car handles the complexity of shifting. What surprises many drivers is how much decision-making happens behind the scenes. Modern automatics can change gears faster than most humans, sometimes shifting dozens of times in just a few miles. That constant optimization is why today's automatic cars are often more fuel efficient and quicker than their manual counterparts, especially in real-world driving. A manual transmission puts the driver in full control of gear changes. Using a clutch pedal and a gear shifter, the driver decides exactly when to shift and how the engine's power is delivered. This direct connection is why many enthusiasts describe manuals as more engaging, especially on winding roads or during spirited driving. What often surprises new drivers is how mechanically simple a manual transmission actually is. Fewer internal components mean less weight, lower cost, and often better long-term durability. While manuals are becoming rarer in the US market, they still offer something automatics can't replicate: a constant physical connection between the driver and the machine. Clutch. The clutch is what temporarily disconnects the engine from the transmission, allowing gears to change smoothly. When you press the clutch pedal, engine power is momentarily interrupted, so the transmission can shift without grinding or damage. Once released, the clutch re-engages, transferring power back to the wheels in a controlled way. What surprises many new drivers is how much stress the clutch handles every day. Every start from a stop, every gear change, and every hill start depends on controlled friction between clutch plates. That's why poor clutch control leads to wear, slipping, or a burning smell. The clutch is invisible in daily driving, but it quietly decides whether power delivery feels smooth or painfully rough. Idle. Idle is the state where an engine runs without moving the car. Even when the vehicle is stopped, the engine must keep spinning fast enough to power systems like the alternator, fuel pump, and air conditioning. In most modern cars, idle speed sits between 600 and 800 RPM, carefully managed by the engine computer to stay smooth and stable. What's interesting is that idle is a balancing act. Too low and the engine can stall. Too high and it wastes fuel and creates unnecessary wear. Changes in idle behavior like roughness or surging are often early signs of underlying issues. That's why idle quality tells you a lot about an engine's overall health. Even before any warning lights appear. Steering. Steering is the system that translates your hand movements into changes in the car's direction. When you turn the steering wheel, that input travels through mechanical or electronic linkages to angle the front wheels. Even at highway speeds, a small steering input can shift the car's path significantly, which is why steering precision matters so much. At its core, steering is about trust. A well-tuned steering system provides clear feedback, letting the driver sense road conditions through the wheel. If steering feels vague, heavy, or unpredictable, confidence disappears quickly. That's why steering isn't just about turning, it's about maintaining control and stability in every driving situation. Power steering. Power steering is what makes turning the wheel feel light instead of exhausting. Early cars relied entirely on the driver's strength, but modern systems use hydraulic pressure or electric motors to multiply steering effort. This assistance becomes most noticeable at low speeds, such as parking or tight maneuvers where steering would otherwise require significant force. What makes power steering especially clever is how it adapts. At higher speeds, assistance is reduced to improve stability and road feel, preventing overcorrection. If power steering fails, the car can still be steered, but it suddenly feels heavy and demanding. That contrast alone reveals how much work this system quietly does every time you turn the wheel. Brake. Brakes are what convert motion into heat to bring a moving car to a stop. When you press the brake pedal, hydraulic pressure forces brake pads against rotating discs, creating friction strong enough to slow thousands of pounds of metal in seconds. At highway speeds, a modern braking system can absorb and dissipate energy equivalent to several hundred horsepower every single stop. What makes brakes critical isn't just stopping power, but consistency. Brakes must perform the same way in traffic, rain, heat, or emergency situations. As components wear, stopping distances increase long before complete failure occurs. That's why good brakes don't just stop the car, they give the driver confidence that stopping will happen exactly when expected. ABS stands for anti-lock braking system, and its job is to prevent the wheels from locking up during hard braking. Instead of letting the tires skid across the road, ABS rapidly pulses brake pressure, often dozens of times per second, to maintain traction. This allows the driver to keep steering control even while braking aggressively, especially on wet or slippery surfaces. What really matters is what ABS does not do. It doesn't necessarily shorten stopping distance in every situation, but it dramatically improves stability and control. That's why ABS has been mandatory on new cars in the US for years. In an emergency, being able to steer while braking can make the difference between avoiding an obstacle and hitting its chassis. The chassis is the structural foundation that everything else is built on. It supports the engine, suspension, drivetrain, and body while also determining how rigid, stable, and safe a car feels on the road. In modern vehicles, the chassis is designed to balance strength and weight, using high-strength steel or aluminum to absorb crash energy while maintaining control. What's easy to overlook is how much the chassis shapes a car's personality. A stiff, well-engineered chassis improves handling, reduces vibrations, and makes steering more precise. Without a solid chassis, even the most powerful engine and advanced technology can't deliver a confident driving experience. That wraps up part 1 of our Car Basics series. If this helped you understand how a car truly works beneath the surface, hit like, subscribe, and let me know which term surprised you the most. Part 2 dives deeper into systems most drivers see every day but rarely